Okay, so here we are in our last video for Unit 7 of torque and rotational motion, and to also finish up our AP Physics 1 curriculum. Okay, so conservation of angular momentum. Remember, we talked about this a couple of times that there are three quantities that are conserved in this giant topic of mechanics, right? The first one is energy, then we talked about momentum, and specifically linear momentum, because the third quantity is the one we're talking about now, which is angular momentum, right? And so we've talked about energy in unit 4, we talked about momentum in unit 5, and now we're talking about angular momentum in unit 7. So if the net torque is 0, right, acting on a system, then the angular momentum is constant or conserved. Right. Remember, we always add in that extra little caveat that the net force or the net torque has to be 0. Okay. An example of conservation of momentum is an example when a figure skater is executing one of their spins, right? So when their arms are spread out, right, their moment of inertia is greater, which, if you remember in the last video, we talked about the relationships of um, momentum, inertia, and angular velocity. If I is big, omega has to be small. Okay. Now, when they bring it in, okay, when their arms are close to their body, and if you've watched the Olympics or any kind of figure skating competition, you've seen this happen. When they bring it in, you'll notice that they start turning faster. That's because their moment of inertia now is smaller, making their angular velocity greater. Remember, I and omega have an inverse relationship. So if I have a big I have a small omega compared to a small I and a big omega. Okay. Now, conservation means before and after have to equal each other. So L before has to equal L after, or I before omega before has to equal I after omega after. Okay. And so let's look at the easy way to do is look at a couple examples. Really, we have three examples here. Okay. And so the first question, suppose an ice skater is spinning at 0.800 revolutions per second with her arms extended. So she's out here big. She has a moment of inertia of 2.34 kilograms times meters per second square with her arms extended, and of 0.363 kilograms times meters per second squared with her arms close to her body. These moments are based on a reasonable assumption about a 60 kilogram um, skater. What is her angular velocity in revolutions per second after she pulls her arms in? And then what is her rotational kinetic energy before and after she does this? Okay. All right. So first one, right? L before equals L after. Sorry. So we're going to do, right? L before equals L after, which means I before omega before equals I after omega after. Okay. And so we're looking for omega after. So omega after will be I before omega before over um, I after. Okay. All we're going to do is divide the after before. And so for right now, we're going to keep it in 0.800 revolutions per second, but we're going to have to convert it for part B. And so with her arms extended, she has a moment of inertia of 2.34, and then she brings it in. She just gets 0.363. So before we do actually find the numbers, we know that this should be a larger omega, right? Because arms extended, we know her moment of inertia is high, which makes her speed small. With her moment of inertia small, we know her speed has to be big or bigger, right? Because it's not going to be um, a giant difference, right? And so her speed is going to be 5.16 revolutions per second. Okay. So to do the second half, our omega needs to be in radians per second. So we're going to do 0.800 revolutions per second. All we're really going to do is have to multiply this by 2 pi, because 2 pi radians is 1 revolution. Same thing with the 5.16, right? All we have to do is multiply it by 2 pi, because 2 pi radians is 1 revolution. And so 0.800 is 5.03 radians per second, and 5.16 is 32.4 radians per second. And so now we can find her K before and her K after. Okay, so we're expecting her kinetic energy after to be greater, because despite the smaller I value, the omega is considerably bigger, right? So we're going to say K is 1/2 I omega squared. So it's going to be 1/2 times 2.34 times 5.03 squared, and that gives us 29.6 joules worth of energy. And now let's find her after energy. So it's going to be 1/2 times 0.363 times 32.4. Again, we need to convert to radians per second, right? And so you can see she gains roughly 160 something joules, right, of energy by bringing her arms in. Okay. Now the next two questions are going to really deal with, kind of these rotational collisions, if you want to say. And so the first question: you have a student visiting the playground with their friends, decides to run and jump onto the merry-go-round. The merry-go-round has a radius of 3 meters and a rotational inertia of 450 kilograms times meters squared. The student has a mass of 60 kilograms and is moving at a speed of 5 meters per second, tangent to the edge when they leap onto the stationary merry-go-round. What would be the angular speed of the merry-go-round and student after the leap? Okay. And so, couple things we need to do here, right? So what happens is, really, the rotational inertia of the system before is only provided by the student, right? And so if you want a physical picture, here's before, right? The student's running like this with a velocity, and this is not rotating yet, right? And so our omega would be 0. And then afterwards, the student is out here, and now it's rotating. And so once they jump onto the circle, it's transferring its MVR onto that onto it. So this is like a inelastic rotational collision, right? In some way. So our initial, or our before angular momentum will be MVR, and our after will be I omega F, right? And so we're going to say MVR equals I omega F. But something that we have to do is, this is now, because now they're one big system, we need to find the total moment of inertia. Sorry, I forgot to write I omega F here. And so the total moment of inertia will be the moment of inertia of the merry-go-round plus the moment of inertia of the child. Now, the moment of inertia of the merry-go-round they give us, right? It's just 450. The child is now going to be treated as a point mass at that distance, right? At that radius. And so the general equation is just simply mr squared, right? And so we're going to do 450 plus a 60 kilogram child out at 3 meters, right? And so this is going to give us a moment of inertia of 990 kilograms times meters squared. Okay. And so now we have all the information we need. So we're going to do MVR over I total, right? And so this is going to be 60 times 5 times 3, because that's the child, right? Over 990, which is the moment of inertia of the system, right? And so it's going to be moving at 0.91 radians per second. Okay. So again, right, if this is right the way you think about it, the system, the child merry-go-round system, okay? So before that child actually hits the merry-go-round, the only rotational aspect is what that child is bringing. So it's going to be MVR. So once they get onto the merry-go-round, right? They're transferring MVR worth of angular momentum onto the merry-go-round, and now they start spinning, right? And it's just like when we had the two trains, right? One train moving, one not, and they stick together. They're now going to be one giant mass afterwards. And so remember, the rotational equivalent of mass is rotational inertia or moment of inertia. This next question has a very similar kind of feel to it, right? And so we have a disk with a rotational inertia of I spinning on a platter with an angular velocity of omega. While it is spinning, a second disk, which is identical but not spinning, is dropped onto the first disk. So here's our initial, or kind of our um, picture, right? So this is spinning. I have a second disk, same. So this has a moment inertia of I with an angular velocity of omega. This has an a moment of inertia of I where it is not spinning, right? And I know they're saying I's and omegas and so forth, right? And so after the second one is dropped onto the first one, and so now we have, sorry, I had the arrow going the other way. So now we have both objects now spinning, right? Um, and so we're asked to find what is the omega of this system, right? But the total I will be 2I. Okay. And so the way you think about this would be like or sorry, not I, but L. So L of disk one plus L of disk two equals L after, right? But L of disk two is 0. And so you say I omega equals I total omega final. Okay. Or I, we call it I. In fact, they call it, this is not omega f, but omega prime. And so we're going to say omega prime equals I omega over I total, but I total is 2, right? And so I over omega would be 2 I, but look what happens, right? And so omega prime is 1/2 of omega. Now you could do this with the factors of 1. You know that the angular momentum does not change. You know the I goes up by a factor of 2, right? And how does omega is that affected? Right? So omega is 1/2 times the original. Okay. All right. So not only does this end the unit, this also ends the AP Physics 1 curriculum, right? And so just it's been fun teaching you. Just have some confidence on that test, and I'll say good luck on the AP Physics 1 test in May.